All right, so here we go. So let's look at the first part of the assignment. So, all right. So problem one. This one was like all of them is like one post if you want that is fixed to the ground, and it looks there's another one here. Oops. All right, so let's see what we had on this one. We had a force of 1,000 newtons. $1,500 newtons, and basically here they were making a cut somewhere over here. Let's say you make the cut over there, and they were asking you about, I think, the stresses at point A, and the coordinate system, I think, is basically Z. Then the Y is parallel to the 1,000. And the X is parallel to this one here. So I want to try to go in detail on this one, okay? So we're doing one of these problems. And basically the question, and then I need the dimensions. So I'm guessing the distance between this point here and this axis was given to be 200. This is in millimeters. Then the length of this one is 400 millimeters. And the cross section. The cross section would be with axis would be, let's say, do X and Y. They give us the radius are equal to 20. Okay, and the question is to determine the stresses at point A. Correct me if I do something wrong, okay, with the data. All right, so on the example we did in class, what is the first step you need to do? Okay, so step one, perfect. Let's look at the loading. Okay, guys, that's something important for me in this class and all my classes is that you learn procedures, that you learn, you take good habit about how to solve problems, no? So first thing, let's say loading. It doesn't have to be loaded, okay? But let's say we do loading in this case. So what is the way we did it? So what will be the origin of our reference frame? Will be the point here at the cut, no? So we go at the cut, then we need to find the position vector, let's say, on point. So this is A, I think I call this point here B. What will be the coordinates of that point? What will be, I mean, this is what will be the Z? 200. What will be the Y? 100, and they're on the same plane, so what is the X? 0. Okay, I'm going to do the learning this way because I think it's the easiest way, no? Instead of doing how you do in statics, see what happens with the moments. And then the vector force, that one is a lot easier. So is it any component on the X? Yes. What will be the value on the X component? Negative 1500 on the Y, 1000, and on the Z, 0. So that's the forces. Then we can calculate the moments by doing what? By just taking the definition, the R cross B. So this will give you what? I, J, K of what? 0, 400, 200, negative 1500, 1000 and 0, no? Okay, so if you do here just this moment, what are you going to do over here? You're going to get 400 times 0 minus 200 times 1000. So that will be what? Negative 200,000. Okay. So the next one will be negative. So we have 0 times 0. So it will be positive. So it will become again negative. So 1500 times 2 will be what? 30 plus 4 zeros. So will be, I guess it's 200,000, negative 200,000. The last one will be what? 0 times 1000 minus 1500 times 4. So 15 times 4 is 60. So 6,000. And if you want units for this will be newtons, units for this will be Newton meters. Okay, so this is something that I do different than the textbook myself, but it's just because it's the way I think about it. But remember, this will be what? This is the external forces. And this will be the external moments, no? Okay. All right, so if we look at external, basically you want external here. I mean, I like to do this. I think that's what I did the first example in class. We'll explain now what. So basically we do the external. So let's do one for each. I don't want to put too much on each diagram. So let's say we have here the E, Y, X, Z, Y, X. So basically here will be the forces. So if we have the forces, what are the value of the forces that we have? We have 1500 over here, no? Yeah, going negative 1500, 1000 on the Y. And that's it. Okay, now on the Z, what do we have? We have negative on the X. So what does that mean? That means I would be going clockwise. This will be here. Next goes clockwise, and this will be the 200,000. So let me put here maybe 200,000. Maybe it might be easier. Clockwise, what about the Y? Again, is negative, so we'll be going clockwise. What about the Z? Counterclockwise. 600,000. Okay, but these are really the external loading, no? Which I don't mind working with external loading because for me, the only thing about structures, I think it's a lot easier for me to understand is that if let's think about the 100 Newton force. If I'm putting this on the outside, I'm doing the external force, the structure inside is going to try to do what? Resist it. So if you can to resist it, and then what is the equation we use all the time is summation of forces equal, it needs to equal to 0. So the force will be equal in magnitude but opposite in the direction, no? So really, if you look at the internal force, it will be just the opposite, no? What about the 1500? Same thing, and the moments the same thing. So basically, the structure will be doing the opposite of what you're doing external because you are trying to counter-react it. Does that make sense or not? Okay, so I like to work with these ones, but when they derive the equations that they give you on the books, they give you the equations with ends and these, no? And those are supposed to be internal, so bending moment, which is internal, and V, which is the shear force, no? Okay, so let's do that just to show you the difference. And again, that's why I like the signs because it depends on which one you use. I rather do the. So then if we do the internal, okay, so it's going to be something similar, but let's use just one thing on the figure. Will be here. Y. X. Z. Y. X. So really, if we look at this, okay, what should be our normal sign convention for everything? You have here, this will be MZ counterclockwise. This will be MY counterclockwise. This will be MX counterclockwise. This will be, if you want, I do it maybe dx, dy, vz. Okay, and we will have again the same forces right here. This will be the 1500. Here we'll have the 1000. Here we're gonna have the negative 600,000. I'm just copying that from the same figure. Here we're gonna have the negative 300,000, and this will be, I think, no, that was one of them was positive, so 600. The 600 is positive, correct, and this one is negative 200,000. Again, to me, it doesn't make any difference, but I want to point it out, okay, the difference. So, for example, now what happens? If you do summation of forces on the x equal to 0, this is going to give you what? Dx equal to what? 1500, no? Should be the opposite on the other one. If you do summation of forces on the y equal to 0, what are you going to get? The y will be equal to what? Negative 1,000. So since there's nothing on the z, we're not going to do it. Now, if you take the summation of moments, let's say the x-axis. So this time, what are you gonna have? You're gonna have, let's do one in detail. So we give you mx minus 200,000 equal to 0, which is going to give you MX equal to 200,000. No, I mean, just change the sign, no? But you see why? And we do the same thing if you want. I'm not going to do that much. On the y equal to 0, this will give you, let's see, my. How much is on the y? So negative minus 200,000 equal to 0 will give you my equal to 300,000 newtons per millimeter. And then we do the last one about the z. Will give you what? mz plus 600,000 equal to 0, which will then mean mz equal to negative. Where here v is what? Vx, dy will be the, now will be redundant to say internal shear forces. Then let's do some understanding. What are mx and my? What type of information are they going to cause? So this should be the internal then the moments, and the mz really is what? It will produce what? What type of deformation will produce? Should know? Yes, so it will be the internal torque. So that's the reason why I don't like them. Remember, I say I'm not going to use signs. I want you to understand the sign by looking if one point is in tension or compression, no? It's because you see that you can use both of them, and but if you choose one or the other, it's going to switch the sign, no? Okay, because the way here, this is what you do, and in this one, what I like to think about this one when I solve this problem is what? Summation of external forces will be counter-reacted by whatever happens inside, no? And I do the same thing for the moment. Does that make sense?
When I did this problem, I didn't even like find reactions, I guess. I kind of just did it by inspection.
Yeah, you don't need the reactions.
Okay.
You don't need the reaction because this is the same thing as we do with the problem with the beam. You can start from this end and you make the cutter here. But if you want, you can, if you find the reaction will be equal to what? Basically to all these forces that we just found over here.
Right. If you found the reaction, we would just start from, in this case,
So you will have all the values here, but it will mean that we make the cut from here to the top instead of from the top to the bottom. So if you do that, it's the same thing as we're doing with the beams, with the distributed load, that you can choose which side you're going to run from. No? Yes, procedure is the same. All right. Mind you, this could be a cantilever beam, no? You can decide not to calculate the reactions here and just start from the right and make the cutter here, no? So you don't need to find the reactions, correct? Or if you decide to make the cut from the left, then you first need to find the reactions. So in this part, you could do it both ways. You could go and find the reactions as well if you want. Okay. All right. So personally, I do this, okay, to tell the truth. But if you really want to use the equation, this is what you need to do. Okay, so we did this. Next thing, what is this? I think on the example in class, what was step 2? I think that's what it was, cross section. This and the first step that we did, this one, so for me, I think is the most difficult. I mean, if you don't get this step right, everything else is more or less useless, no? Yeah. But I mean, you can be the best stress analysis, but the difficult thing in doing stress analysis is not to find the stresses, is to know exactly what are the loads being applied at that section. All right. So this is the most important step. That's why I'm being picky about that you learn how to find the load from the distributed loading, no? Okay. All right, so step 2, cross-section property. So in this case, pretty easy because what we have a circular cross-section, no? At the cut. So to tell you that I don't know the whole properties over here, you might need to help me. So it's circular with radius r. So again, over here, so the area is easy. Area will be 5 r squared, which I think I calculate to be equal to 1.2566 10 to the 3 millimeter square. Then I call this one I, but basically this, let's make here the detail. But let's think about bending. About which axis can this bend? So we have here the Z, Y, X. About which axis will this be bent? Either on the X or on the Y. But since it's circular, what does that mean? That basically X will be equal to I, Y, Y. And I just call that one I. And that one I have to look at it is pi over 4 to the 4th. And this will give you 1.2566 10 to the 5th millimeters fourth. Check the values because you should have these values on your assignment, no? Okay, and then you have to help me. This one, J, is it twice or half?
It's 2 times. The denominator is that. So it should be pi over 32 e to the 4th. Doing radius 5 over 2.
So it's pi over
2. 5 over 2.
pi over 2. Okay. So basically it's twice this one then, no? Whatever that is.
2.5, 1.3.
Okay, 2.5. Yes, what else?
133.
133.
And then my units are in meters, not millimeters.
So that should be 10 to the 5th. I can work with that. Millimeters to the 4th. I think we needed one more thing for this one. That's what I decided to do with you in class. This one I was looking at. What is it? Okay, yeah, and I think I just got this stuff yesterday evening in the assignment, no? Is that if we look at the semicircle, so that semicircle, what will be the location of the CG of the semicircle over here? Yeah, I call that distance C. So CG of semicircle, I call that one C, is equal to 4R over 3 pi. Oops, can you see now? Yeah. Okay, and I could do here the Q's, but I'm gonna do it later so that we have different figures for them, okay? For better understanding. All right. But you could put them in that step, which is actually what I did on my solution, but I think it's better to put them later. Okay. Any questions so far? Remember, in class is the time that we do everything together, no? You can ask as many questions as you want. Now, step 3. What is step 3? We're gonna find the stresses, no? I think that's what I did on the example English. I'm trying to follow the time the same procedure. So what type of stresses can you have? Axial, normal, and shear, no? Yeah. Okay. In this case, maybe we can skip a little bit. Do we have? I mean, there will be normal as well. So let's look at it. Okay. So we have. Let's first look at the. Normal stresses. So if we look at the figure, again, I don't know the relation by heart, but you can come out. So what is the direction of the normal stresses or the actual stresses for the section here? See? Yes? Okay. So books can give you different. So now, you see, you can have stresses due to what? Let's say to a force coming on the C, no? Yeah? So let's say we have VZ divided by A, but in our case, we have a VZ? No, so they just say right away that this one will be equal to 0, okay? For the math, okay, some books will start giving signs, but I'm not going to put everything positive. Remember, I will tell you, look at the sign from tension compression, no? Now, what is the other thing that can create here? Normal stresses. Okay, bending. So let's look. You want to look first about the bending of which axis? First. Okay, so it will be then mx. So the moment mx will be bending about which axis? About the x. Do you see that or not? So you don't need to memorize the equations. You just need to understand it. When you apply this one, we'll be bending about the xx, no? And if it's bending about the xs, then so this will be the axis over here. Then you have to look at the location. What will be the distance? You have to look at what distance out there. What will be the x-axis? Will be right on the x-axis, no? So we have to look at the one. Does that make sense or not? Can make that understanding? Now, what is the other look that can create normal stress? Will be the other bending. So we have an X that will be created by the 1000 Newton force, and then the 1500 we create a model of the rate. So again, this time the will be bending on which axis? The C or the location will be dictated by what? By X. You see, even if you don't memorize the equations, you can figure them out with understanding. And remember here, sign given by tension compression. I don't like to give the sign, but I can put a sign here somewhere, and everything will become good with the result when you use this one as internal forces. But again, I told you how to do that. I want you to do the understanding. Okay, so let's do maybe here one cross section here. Let's do a little sketch. So figure from before. I kind of copying this one here, the one for the moments. We have the Z. We have the Y. We have the X. And from the figure, looks like on A is where? It's already X-axis, no? Okay, so what does that mean? So for example, if we look at the, so let's say if we have what, bending. What is the direction of the bending? That's why I like to use the external forces. External force given this one here of 300,000, no? And the MY is this way. 12,000. Okay, so let's first do. So what happened with this term? Moment about X. All right. We need to, so what will be the neutral axis? Will be the x-axis, no? What will be the stresses along the neutral axis? Zero. So basically, why this system will be zero? Because the y is zero, no? Yes. So you see here, this is zero, so whole term will be zero. Do you see that? Okay. All right. Now, this point over here, now the my, you see, now this one will be the neutral axis now, will be the y-axis, no? So what would be the distance x? What would be x?
R.
Okay, r. Now, if this is bending, so this will be creating a bending, this is a y in that direction. Okay? So point A will be in tension or compression? Tension. Do you agree? Do you agree? Yes, okay. Everybody agrees? You see, I'm not looking at the sign, no? You could make this work with the signs, but it's so easy to get the wrong signs that I rather do that with understanding. So this term should be in tension. Okay? So if we substitute, we're gonna get here sigma z. I just look at the magnitude, so we only have the M1, which will be 300,000. Times 20 divided by the, what was the value? 1.2566 10 to the 5th. Which is giving me 47.7465. You want, I mean, I did that with MATLAB, so it's newtons millimeter square. Okay, all we could do now what? Okay, one is how many millimeters? 1,000. So if you put this square, okay, we remove the millimeter square, no? So this will give you that sigma z is equal to 47.7465 megapascals. Any questions so far? Everything makes sense? Okay, the important part here is the understanding. Okay, the equations, you're always going to find them. Or you can see, you can re-get the equation with understanding, no? Okay, so now we did the normal stresses. What will be the other stresses we can find?
Where would be,
What?
I don't know if that's that unit for is right. Is it the 1,000 times 1,000?
She did square on the.
Is a square. That's why I did it that way. That you see, you can just put this one and put the square on top. No, but good question. So that's why you have this is 10 to the 3 times 3, which would be 10 to the 6, no? That's where you get the mega. All right. Okay, shear stresses. So that one's a bit more difficult. I understand. And I get it, okay? And I get it. So the general equation for this is what? Q over IT. Yeah, that's a general equation. All right. Okay, I'm gonna put here another equation that I have. What is the definition of Q is? First area moment of inertia, but we say Jan is equal to area times whatever. Let's say y central. Just put central because it might be different, no? Area times central location, no? Okay. Okay, so here we have different cases for V. Correct? So what do we have? Let's first look at, let's say, the V, and that's why I don't care here which one you want to use. I like to use the external, okay, to the truth. So that's why I like to use the external, even though. Okay, let's use. That part here, V. Let's say V, let's still use Vx then. Vx. About negative 1500 for me, but since it's 1500, we get the same thing, doesn't matter. Okay, so let's do again a small figure. Figures are extremely important. So that's from where you're gonna get what's happening on the problem. So let's forget about the Z. Is that okay? Can I just forget about the Z? So this is 2D, this is not pointing out, no? This is just a cross section. So if we do it that way, with our point A is over here, no? Is that okay with the figure? Okay, so if we look at the force Vx, so in this case, this is internal force. So we'll be coming here, the Vx will be coming this way, no? And this is internal action. So what will be the shear? So basically we have the equation here. Tau xy if you want will be equal to Vx times Q, let's say Qx, divided by I. About which axis will this be bending here? Will be going to cross section. It will be the Y, no? Yeah. And T. But in this case, what's important is that if the force is coming this way, what will be the shear? What is shear? What is the definition of shear? What needs to happen in order to have shear? Okay, but without definition, just common sense. You need to have one surface rubbing against the other one. If the force is going this way, is it any surface rubbing against another one at point A? Okay, it would be the same thing as you had point A on the other side, no? Correct? So what would be the shear then at that point? 0, because what is 0 here? Because your Qx is 0, no? Yes or no?
Yes.
Same thing as remember when we had the rectangular cross section at the top and the bottom was 0, no? The surface is also allowed to have the top and the bottom. No? Yes.
Since the Y bar is like a centroid location, how does that work mathematically? There's still a centroid in that area, right?
Yes, but what happened? So what? But there is no area.
Oh, I see.
Okay.
So what area do you look at for a cube?
Okay, we'll just do it on the next one. Okay, we'll look it up. On this one, there's no area, no?
Right.
Okay. So now for the next one would be what? The V, I guess would be Vy, which I think should be equal to the internal. I like to use the external, but anyway, we started with this. So internal is nearly 1000. Let's do again the figure. On A. So this time, what is the force coming? Nearly, so it's coming down this way. And point A is over here. So what will be the area? Area of half the circle, no? Yes? Would be your A, and now you need to find the center of that distance from the bottom here, which is C over here, and I give you what was C, what was C. 4/3 pi. So then what does that mean? In this case, then the Q will be equal to what? Will be L times the C, which will be equal to what? Pi R squared divided by 2 times the distance to the central to that area, which will be 4R over 3 pi. Do you understand this? Okay, so now basically we just consciously write here tau xy if you want, it will be equal to what? So will be equal to V. Now we do what? The Vy Qy over IT. Oh, we should have done maybe the T. So this should be equal to what? Vy is equal to 1,000. Two parts. We're already doing it that way, so it will be 1,000 times, I don't know what Q is, okay? So Qy, whatever that would be.
5.33.
5.23.
5.33.
5.
5.33.
Oh, okay, 5.3333, okay. Should be what here, millimeters?
I have it in meters again, it was in the -6.
Oh, be careful because this is cube now.
Yeah.
So I don't know, so this is to the meters or
No, that's correct.
That's right.
in millimeters? Yeah, I don't know.
Yes, sir.
I don't know.
No, because it's not 10 to the 6, it's 10, this time is 10 to the 9.
10 to the -3rd.
Yeah, so I think 10 to the -3, no?
Yes, sir.
Maybe somebody can do it, but 10 to 93.
I have 5.33 times 10 to the -6. Yeah.
So it's the same as the.
He's
Trying to convert it to millimeters.
So what did you get in millimeters?
I didn't calculate it in millimeters. I put my.
Oh, and somebody do it in millimeters?
Yeah, it's 5.33 times 10 to the -3rd.
Okay. All right, thank you. Okay, so basically now you substitute here. This was the I we say was the IXX, which is the same as the other one, 1.2566 10 to the 5th. And now maybe something I can put, what would be T? What is T? T will be the width of the shaft, no? Yeah? What's the thickness? Which will be 2R. So this will be 40.
Wouldn't it be 5.33 times 10 to the 3rd? Yeah, it's third, not -3rd.
Ah, okay. Since you say 0.5, okay, so 10 to the 3. Okay, so for this one, I'm gonna have the result. Give you after unit transformations. One, but go and check 0.61 megapascals.
Oh, why do we drop the negative there?
Because okay, let's look at it. Let's forget about the sense, okay? That's why I say forget about the sense for 1 second. I like to look at the other forces. So you agree this one is like if you want to internal, so it's the opposite of the external, no? So this is the direction of the process. So in what direction will the stresses going? The shear stresses, in what direction will be going? It will be going down, no? So let's say this will be, to say this, saying this, let's say will be negative y direction. Can I say that?
Okay, I got you.
That's why I like to use the science. Okay, it's a lot better to go understanding, no?
Yes, sir.
The problem is that when you start programming, if you need to program with a sign criteria, no? And that becomes complicated, but for the understanding, I think this is the best. So, so what else we have? We have left now the last force, which was the moment about the Z, no? Okay. So now we will look at VZ. The VZ we say was equal to what? To is to a torque. Sorry, MZ. MZ is the moment about the torque, and that one was equal to 600,000.
Yep.
And you see, I don't put signs, okay? But we'll find out now which direction is going. Okay, so let's do here the figure again. Z X Y. Okay. Again, so we're going to use the internal since we did the calculation that way. MZ is negative 600,000. So that means it's going in what direction? Clockwise. So clockwise would be this way, no? Yeah, so if it's going clockwise, that means that the shear flow over here is also going to go same direction. I would like to do the opposite. Personally, I like to say I will put the external. I know the one will be going in the opposite direction, no? So we use this one. So let's see if I need to do this. Okay, let's do maybe now this figure here just with the X and Y. Just to double check something with the Y. X, so we'll be going clockwise. So that means that if we look at the stress, we'll be going this way, this way, this way, and this way, no? It's the same, no? All right, so now this is producing what? This is torque, it's not a force anymore. So that will be equal to what? T R over J. And point A is over here.
Point A is on the x-axis, right? Right on the outside of it.
Yes. So now this one will be equal to what? So we know that T is equal to what? 600,000. I will be equal is equal to what? 20. And you did give me the J to be equal to 2.5133. 10 to the fifth. And I don't know if I did that calculation. I think I did. Yes. And this actually gives me that this is actually the same as the bending moment, which is very strange, as the normal stress.
Yeah.
47.7465.
Second problem has very similar moment and shear as well.
As well. Yeah.
It's very similar.
Okay.
Maybe it's because it's a circular cross section or something.
Yeah, the circular cross section, and now we can talk about that a little bit. Yeah. So you get this one, and this one will be going in what direction?
Down the negative one.
So we're going. How did I put before? How did I wrote it before? Negative y direction. Okay, so if we do like a short summary over here, What can we say? We can say that the normal stress on the Z was equal to 47.7465 megapascals. Since they are going on the same direction, can we add them together? So 47.7465 plus 1.061, which is no idea. 48. 48.8, okay, yeah, close enough, I agree. Megapascals. Okay, so this is the another problem. So no questions, perfect. All right. So one thing about the what is called the polar moment of inertia, J, or some books call it I sub P, okay? Depending on the textbook. So why generally they give you shaft or circular cross section when you deal with torsion? Okay, because when you think about it, the general definition of I or J is what is upon the general here is Y dA, or it could be X dA or XY dA, no? But if you want it to be for the polar, could be, then would be XY dA. Right? So this one, so what happens if you try to find the one that is circular? Yes, you can find an easy relation between how is X changing with respect to Y, no? Yes? So you can calculate it. Now, what happens if you put a square or rectangle? Is it easy to find a relation between the X and Y? No, because that distance is not the same as this one, no? All right, okay. In addition to that, when you go here, the shear flow, you want the shear stress around the cross section will be uniform, no? Will be kind of constant. But if you go through a cross section that is not circular, every time there's a corner, it will be some type of something will be happening at the corners. Yeah. So for example, the polarization of the J is only exact. I'm going to put slash known for circular cross section. For any other cross section is given by an approximation. Is given by approximation. So in most cases that will depend, but you know, is if you have a square Gianni, the approximation will be given to you or defined, all these different data can be given by, let's say, a circle that goes this way, no? Some people approximate, or some people approximate by a circle that goes inside or stuff in between. Okay, or experimental data. But do you understand that the torsion, when you do torsion, the J is only exact or really known for circular cross section? Does that make sense or not? So as soon as you have a circular cross section, you already know that you're gonna have some errors involved depending on the value of J that you take. Okay? And if you need to check the structure, what would be the location where you would need to check for failure or something? What would be the more critical points? Probably you have to look at the corners, no? Right? Because probably it will concentrate over there. So here what's important to know is that you realize that is that the J only accurate or not for circular cross section. If you have something that is not circular, you're gonna get approximations. That's the main reason why almost every single point they give you is a circular cross section, no?
So is there no formula for other shapes?
They are approximated formulas. But if you go to different textbooks, you will see some may have different ones. All right, so what time is it? 51. I'm gonna end over here, that way I can give you back the